In an earlier section, we looked at the expectation, where the expectation is a sort of measure of where the centre of the distribution of a random variable is. In this subsection, we're going to look at the variance, which is a measure of how spread out the outcomes of a random variable tend to be. So let's start by looking at the definition of this variance. So the definition goes like this. Let x be a random variable, and the expectation comes into the definition, so it'll be useful to give that a letter. So let's say it has expectation mu, then the variance is, we call this just var for variance of x is equal to the expected value of x minus mu squared. So mu is this expectation, and we're looking at how far does x tend to be from its expectation measured as a square. Just to be clear, we try to avoid writing brackets when we don't need to. This means the expectation of x minus mu squared. It does not mean the expectation of x minus mu all squared. It doesn't mean that. If you think about it for a moment, that second thing is equal to 0. This means the expectation of x minus mu squared. Note also that because x minus mu is a square, it's greater than or equal to 0, and thus the whole variance is greater than or equal to 0. So variance is a positive quantity, or 0. Okay, so those of you who remember when we talked about things like the sample variance and the sample covariance back at the beginning of the course may not be surprised to learn that the definitional formula we've just written down also has a computational formula to go along with it. So let's state and prove that. So the computational form is that the variance of x is equal to the expectation of x squared minus mu squared. Again, to be clear, this second term means the expectation of x squared, but we try not to write brackets when we don't have to. So let's prove this, shall we? You can probably guess how this will go if you remember what we did in section 1. So the definition of variance is that it's x minus mu squared, the variance of x, and let's expand out that square bracket. So this gives us expectation of x squared minus 2 mu x plus mu squared. Then from the linearity of expectation that we saw in the previous subsection, we can bring the expectation inside the brackets in much the same way as we brought a sum inside the brackets when we were doing sample variance. So this is expectation x squared minus expectation 2 mu x plus expectation of mu squared. And again, we can do things like taking constants outside. So this term, we can't really do anything with that. Here we can take 2 mu outside. And mu squared is just a constant, and the expectation of a constant is just itself. But here, in this middle term, that there, the expectation of x, that is the thing we were calling mu, right? So in fact, this is expectation of x squared minus 2 mu times mu, which is 2 mu squared plus mu squared. So that all comes out. Expectation of x squared minus mu squared, which was what we were trying to prove. So just a bit of monkeying around with the definition of expectation there. So let's see a couple of examples of how to use the definition of variance. So, what about X is a Bernoulli trial, probability of success P? Well, let's try and do this with both formulas, with the definitional and the computational. So for the definitional formula, remember that's the variance of X is X minus mu squared. Well, here you should remember from our previous section that the expectation of a Bernoulli trial is just equal to P. So here this is the expectation of X minus P squared. So by our law of the unconscious statistician, is 0 minus P squared times the probability of getting a 0 plus 1 minus P squared of the probability of getting a 1. That's because the possible outcomes are 0 and 1, but because we have an X minus mu, we're doing an X minus P there and there, and then times it by the probabilities, because that's how you get an expectation. So this, well, the first term 0 minus P squared, that's just P squared, and the probability X equals 0, that's the probability that the Bernoulli trial is a failure, which is 1 minus P. And there's 1 minus P squared, and the probability the Bernoulli trial is a success is P. So both of these terms have a P 1 minus P, don't they? And then the first term has another P, and the second term has another 1 minus P, but the P's in that big bracket at the end cancel each other out. That comes out as P 1 minus P. So the variance of a Bernoulli trial is the probability of success times the probability of failure. We could also have done this using the computational formula. Let's just do that to show that we can. Under that one, the variance of X is expected value of X squared minus mu squared. So here, the expected value of X squared is 0 squared px of 0 plus 1 squared px of 1. Again, by the law of the unconscious statistician. And mu is P. So 0 squared times anything is 0. 1 squared times anything is that thing itself, which is the probability of success, which is P. So we get P minus P squared, or if we take a P out of the brackets, it's P 1 minus P again. Maybe the second method was slightly shorter than the first method, but not a great deal in it. Similarly, for X being the dice total, well, we saw that the expectation was 7. You can do the variance of X's. I think I'm going to do the computational form again. So, this is, I won't write out the whole thing, but 2 squared times the probability of getting a 2, which is 136. 3 squared times the probability of getting a 3, which is 236, etc., all the way up to 12 squared times the probability of getting a double 6, which is 1 over 36, all minus 7 squared, because 7 was the mean. And if you work all that out, there are a few more details in the notes. It comes out as 70/12, which is 5.8 or so. So those are just a couple of examples of calculating the variance of some random variables. In an earlier section, we saw what happens to the expectation of a random variable if you multiply it by some number, say A, or if you add some number, say B. So let's look at what the equivalent of that for variance is. So, theorem, the variance, if you multiply a random variable by A, you can bring the A outside the variance, but you have to square it. Is A squared times variance of X. Similarly, if you shift your random variable by B, that doesn't change the variance. You can think the spread of your random variable doesn't change if you just move how big or how small the random variable is. I'm not going to prove either of those statements, because those statements will be for you to prove on problem sheet 3, I think it's perhaps question 5 or 6, where you can prove those statements about the variance.